Hi, welcome to week 8. This week we're going to be focusing on a new system of derivation. It's in one sense new because we're going to be using new rules, but in another sense we're just going to be building up from our old system. So before we had our system SD, and now we're going to be working with a system called SD+. And before I tell you a little bit about some of the new rules that we'll be introducing, it's important to note the following. So remember, we've used the single turnstile here to mean proves that. And so if you have a sentence like gamma, then we say that we can prove from a set of sentences where our primary assumptions will be here, we can prove some sentence P. That's what this symbol says, this single turnstile. This says from a set of sentences here, you can prove some sentence here. Or in other words, you can derive the sentence P from the set of these that contains the premises of this set of sentences. And one of the things we'll have to keep in mind is the extra rules that we add don't give us any power. In other words, if a sentence P is derivable from gamma in our regular system SD, that's the case if and only if. So this is a biconditional, right? If and only if P is derivable from the same set gamma in SD+. So what this basically is saying is we're not going to be able to prove anything more than we couldn't have already done beforehand. Vice versa. So anything that's derivable with the rules that we have in SD+, they're going to be derivable in SD, and anything that's derivable in SD is going to be derivable in SD+. So just keep this in mind when we're introducing these new rules. We're not actually getting any more power out of the derivation system. So you might ask then, well, why are we going to add SD+? Well, or why are we going to add these extra inference rules to create the system SD+? And the answer is simply that it's going to make our lives a lot easier. Up to now, we've had to do a lot of work to get some of the derivations that are relatively that can be done in a relevantly more simple manner. So what we're going to do now is introduce ourselves to some of those extra rules and see how they move a little bit faster. So let's start with a blank page here. The first one is called, let's do this with orange. This one is called Modus Tollens. And actually, one of the things I should mention is the rules that I'm going to tell you about right now, they're called rules of inference. So I'll go over the 3 different rules of inference that we're going to introduce for SD+, and then there's other kinds of rules that we'll introduce in a separate video. So up to now we had we sometimes had scenarios like the following. You'd have some sentence like if P then Q. And you could do something like assume Q, you derive some kind of contradiction, where I'm just using this symbol here to mean a contradiction, so you get like A and not A, to give ourselves not Q. So at some point we might have had not Q, and we can actually, let's just shorten this up here. So assume that at some point I've gotten not Q as a sentence. Well, we know that if you have if P then Q and not Q, that this then entails not P. But the way we would have had to do that up to now in our system is to assume that P is the case, then derive Q by conditional elimination from the line up there, and then we'd have to get not Q by reiterating that here, and then we could actually get not P. So we have these 3 extra steps that we'd have to do if we wanted to get not P. What Modus Tollens lets us do is it just says, you know what, maybe I'll actually scratch this out. Modus Tollens says, you know what, let me give you a shortcut. We'll let you go straight from if P then Q and not Q to not P. And the rule here is Modus Tollens. And this is how we use the justification. So we would cite, if this was line 1 and this is line 2, we would then say Modus Tollens on line 1 and line 2. Okay, so when you have a conditional and you have the negation of the consequent, then you have not P. Don't confuse this with the other rule that we have called Modus Ponens. And in fact, Modus Ponens is actually just characterized by our rule of conditional elimination. So up to now we said, look, if you have P and you have if P then Q, then you can actually just get Q by conditional elimination. This conditional elimination effectively is Modus Ponens. But don't confuse this with Modus Tollens, which says when you have the negation of the consequent, then you can derive the negation of the antecedent. Okay, so that's Modus Tollens. There's 2 more that we're going to go through here. The next one is called Hypothetical, and I'm not going to write this whole thing out because that'll take too long. So it just is Hypothetical Syllogism. And we've already made a proof of this as well. Actually, you'll recognize it. So hypothetical syllogism basically lets you go from a sentence if P then Q, and another sentence if Q then R. It lets you go from these sentences straight to if P then R. And the justification will be HS, which stands for hypothetical syllogism, and then you have to cite these 2 lines. So in this case, line 1 and line 2. So remember, we had to do this the long way up to now. The way we had to do this is if we wanted to get if P then R, we would have to first assume P. Right, so suppose we're over here in a derivation. And suppose I have if P then Q, and I also have if Q then R. So suppose I have this in my derivation somewhere. In this case, we'll just say it's our premises. Then to get if P then R, right? If our goal is to derive if P then R, we would first have to set up the subderivation to be able to do conditional introduction. That was our goal. So you take the antecedent, you make that your auxiliary assumption, and you make the last line of the derivation, you make that R. And then what we'd have to do is, well, we'd have to cite 1 so that we could get Q by doing conditional elimination, citing line 1 and line 2. It's a little messy there. And then we'd have to use again, conditional elimination to go from 2 make sure I number this line here. To go from 2 and 4 to get R. So we'd have to again use conditional elimination. This would be 2 and 4. And then we could do conditional introduction, citing line 3 to 5. So this is what we had to do beforehand. But hypothetical syllogism just says, nope, we don't need to do this extra little step right here. Actually, you still need those ones up there. Sorry, I shouldn't have erased that. But it says, no, look, you don't need these guys. That's all right. You can just skip ahead right to this, since we've already proved that. So that's hypothetical syllogism here. You have these 2 somewhere along the line in your derivation, and then you can just go from if P then R, citing hypothetical syllogism. And let's do one more. This one is called Disjunctive Syllogism. I need to make this a little bit smaller here. Okay. So this last one is called disjunctive. and I won't write out all of syllogism again. And it looks like this. Suppose you have a sentence P or Q. And then you can show at some point not P. Or alternatively, you might have shown not Q. You can then say, therefore, Q. So this is the inference you're allowed to make. And the alternative, as I suggested before, is you might have P or Q, and you might get not Q. Well, from that, you can then derive not P. So let's think about why this is the case. When we have a disjunction, we know that at least one of the disjuncts has to be true. And then in the second line, we're told, wait, one of the, this disjunct in particular is in fact not true. But since this whole disjunction was true, and we were just told that it's not the P that's true, then Q has to be the one that's true. And similarly over here. So we're told, look, P or Q, right? John's at the party or Sally's at the party. And that whole sentence is true. And somebody says, look, Sally's not at the party. Then you know that, oh, geez, that's wrong. Then you know that John's at the party. Oh, glad I caught that. Then you know that John has to be at the party because the sentence, the disjunction was true, and we're told now that one of the disjuncts is not true. So this also helps us shorten things up a little bit as well. So if you think about how we would have had to go about this, maybe let's do a quick example. So suppose you had, A or B. And at some point you're told, hey, guess what? Not B is in fact the case. How could we actually get A? Well, we'd have to do an extra step. So we can use, we'd actually have to use a couple extra steps. We can use disjunction elimination, right? So we can do what we ordinarily think of as our proof by cases. So we assume in the first case that A is the case, and then we assume later that B is the case. And our goal using disjunction elimination is to get A in both of our subderivations. So we want to get, I'll bring this down, we want to get disjunction elimination, citing 1, and then these two subderivations which we don't yet have numbers for. So in the first case, our goal is to get A, and in our second case, our goal is to get A. Here, we're already done, right? Because this is just reiteration from our actual assumption. So if this is line 2 and this is line 3, then line 4, we can just cite line 3 as reiteration. So we're done that first subderivation. Now we need to do the second subderivation, and we need to get A. Well, I mean, we can't get it from B, and we can't get it up here, right? Because this is a disjunction, so we can't just eliminate that side. That's not a valid rule of inference. So given that we don't really have any other options left, a good strategy is to use negation introduction. So we'll do another subderivation where we'll assume not A. And we're going to do that for the purposes of negation introduction, or sorry, negation elimination. And here our justification will be negation elimination, and citing this subderivation. So we won't know which one that is, but it'll be from 6 to something. And notice, remember the rule for negation elimination, the thing you have to do is try to get a contradiction. And here, that'll be relatively easy. We already have, in the scope of this subderivation, we already have B. And we also notice that we have not B up here. So in both of these cases, we can use the reiteration rule, and I'm just going to be lazy here, not fill it in, just so you guys don't waste, I'm not wasting too much of your time. We have a contradiction here, which means that we can then use negation elimination to get that out. So that would go up to line 8. This would be line 9. and then this would be line 10. And then we would have disjunction elimination, citing line 1, then 3 to 4, and then 5 to 6. 5 to 9. So this is how we would have to do it, right? This is a lot more work. Disjunctive syllogism just says, no, look, if you have P or Q and you have not P, then you can actually just skip all of this work right here that we've just been doing. Just go ahead and just skip right there, because we've already proven that this is the case. So before I finish off here, let me just make a point of giving a name to the rules that we just gave. So these were rules of inference. And there's going to be a few other rules we introduce later on, but the 3 I just gave you were the rules of inference. And just as a test, you should become comfortable with the short form notation that we've picked of them. So Modus Tollens we just had as MT, and you should hopefully be able to remember what rule that is. We also had Hypothetical Syllogism, which we just abbreviated as HS. And then we also had Disjunctive, oh man, let's try it over here. Disjunctive Syllogism, just as DS. So make sure you feel comfortable with these abbreviated versions of the rules so that you remember what they are in the future. And in the next video lesson, I'm going to cover rules of replacement.